Great, so I'm talking about sparse if-then rule models. And my goal over the last few years has been to try to produce an alternative to CART. CART is classification and regression trees. I don't know if you're all familiar with CART, but it's one of the top 10 algorithms in data mining. There are more recent alternatives to CART, so C4.5 and C5. CART, though, is the one that's the most widely used. It's basically the kind of the go-to method for interpretable classification in industry. And it works very well, but it's very greedy. So for instance, if I wanted to predict whether I'm going to get stuck in traffic on my way home from work, then maybe I would collect some data about my trips home. And then if I was using a decision tree like CART or C4.5, I would say, OK, what factor gives me the most information about traffic? What's the most informative feature about traffic? OK, rain. All right, I'll split my data set into two pieces based on rain. And then I'll kind of recursively keep splitting, kind of myopically, and split the data into many, many pieces. And then I would go back and greedily prune nodes that I think I don't need. OK, so the whole thing is sort of top-down greedy, which means that if you make a mistake at the very top, you spend the rest of the decision tree trying to undo the mistake at the top. And that's what I'm trying to avoid. OK, so it works well, but it's greedy. Just a note about interpretability. So interpretability is very context dependent. There's a large literature on interpretability. For the purpose of this talk, perhaps it means concise or sparse and convincing. We want to give people reasons for each prediction that we make. Sometimes linear models, like what we heard about yesterday, are more interpretable than logical models. But sometimes the logical models are more interpretable than linear models. It depends on the context. OK, so I'm going to talk about Bayesian rule lists. So Bayesian rule lists is a method that we designed that's supposed to be an alternative to CART. And the code for Bayesian rule lists is on my website, so you could give it a shot if you want to try it. Bayesian rule list produces decision lists. So a decision list looks like this. This is an example of a list that predicts whether I'll get stuck in traffic on my way home from work. So this list says, well, if there's a game at Fenway Park, then I'm going to get stuck in traffic, because I live near Fenway Park. So if there's a game going on, I get stuck in traffic. And that's true with 97% probability. If there's no game at Fenway Park, then check if it's rush hour. Because if it's not rush hour, then predict no traffic with a 90% probability, and so on and so forth. And everything is going to be learned from data. We're going to learn which conditions to put in the left-hand side of these rules. We're going to learn what order they should go in and what the probabilities are on the right-hand side. There's 3 user-defined parameters. There's the length of the list, so the number of rules in the list. The width of the list, so how many conditions per rule. And then the user's preferred probabilities on the right-hand side. So if the user wants to, they can kind of prefer one label over another. I generally don't use those parameters. So I usually just put in the priors for the length of the list and the width of the list. The way we're going to construct the lists is in 2 steps. And the first step is to mine frequent item sets from the data. So for instance, if we're looking at patient data and we're trying to predict stroke, we might see the conditions diabetes and hypertension together fairly often. Now, this step is easy. There's a 20-year literature on how to do this. There's a million algorithms, and they all produce the same result, which is the set of frequent item sets. And they're all very, very fast. So you just grab one of these things and click, and you get this whole pile of frequent item sets. Now, the modeling part is in step 2, where you have to figure out which item sets to use in the left-hand side of the rules and what the probabilities are on the right. So if I'm predicting stroke, I have to figure out what conditions to put, in what order to put them in, and then what the probabilities are on the right. OK, so there are some benefits of doing this. The first is that as long as step 1 is sufficient, as long as you mine enough rules, then you can get a subset of them and an order of them that's going to be a kind of sparse and accurate model. Okay, so that's good. That basically that's the only approximation you're using, is the fact that you're using these discovered item sets. So this avoids us having to solve a very, very computationally hard problem. It makes the problem much smaller. And then there's an additional benefit, which is that when you restrict to the set of these item sets that you discovered, that might actually make the model more interpretable, because you're building your whole model out of building blocks, each of which is interpretable. And the complexity of the whole model class is actually the same as that of decision trees. So the interpretability is somewhat of an illusion, because if you take a decision tree, you can turn it into a decision list. Any decision tree can be turned into a list. And a decision list is already a decision tree. So you're not inherently losing complexity over decision trees. Okay, so this is how the model goes. There are 3 user-defined parameters: one for how many rules you want, one for how many conditions per rule you want, and then the preferences that you have over the labels, the predicted labels. And again, I don't use these. I usually set them all to 1. And the generative model for these decision lists goes like this. You sample the decision list length from a Poisson distribution centered at lambda. So that's how you get the list length to be approximately lambda. Now, for each rule in that list, you're going to sample its cardinality from a Poisson distribution centered at eta. Okay, so now you know how many rules you have in your list and how many conditions per rule you have. And then what you do is you look through your giant pile of rules, and you pick out the rules that are the right sizes. Okay, so for each rule in the list, you go to the pile, and you choose which item set to use in the left-hand side uniformly over the rules that are the right size. Okay? And then, for the right-hand side, you sample the rules distribution over labels, which is called theta j, from a Dirichlet centered at alpha. And that's how you get the labels to kind of look like alpha, because all the rules label distributions come from the same Dirichlet. And then, for each observation, all you have to do is send it through the decision list, find the first rule that applies to it, and then sample the label for that rule from that rule's multinomial distribution. So if you're working with observation I and it fits into rule J, it's captured by rule J, you get its label from the multinomial distribution for rule J. Okay, so that's the full model. The one thing I have left to tell you is how to sample from the posterior over rule lists. And luckily, for Bayesian rule lists, a lot of the variables get integrated out, so you never, ever have to see them. But there are Metropolis Hastings steps that take you from rule list to rule list. So you can either, if you're sitting at a particular rule list, you can either swap 2 rules in the list to get a new one, or you can grab a rule from your giant pile and stick it in there, or you can remove a rule from the list. And then that's how you sample from the posterior over rule lists. Okay, so let me show you kind of a sanity check, which is the tic-tac-toe data set. So the tic-tac-toe data set is a publicly available data set, and it's just tic-tac-toe boards. Each row of the data set is a tic-tac-toe board after the tic-tac-toe game is finished. And the label for each board is whether the X player won the game. This is a very simple classification task for a human, because you're just trying to see whether there are 3 X's in a row on the board. But the computer doesn't know that. It has to learn it from the data. So this is cart on tic-tac-toe. It's not that interpretable. In fact, I don't feel like explaining it. I also didn't feel like typing it all out on the slide. I got kind of bored while I was typing it, so I left it like that. If you want to see the full one, it's actually here. Still not particularly interpretable. The accuracy is 88%. It's several hundred data points. I can't remember exactly how many. This is C4.5. The accuracy is a bit better, 92.5%. Still not particularly interpretable. And this is Bayesian rule lists. So it says if there are 3 x's in a row this way, then x wins. Else, if there are 3 x's in a row this way, then x wins. And it just goes through all the possible ways that you could get 3 x's in a row, and then it says otherwise, x doesn't win. Okay? So this is the advantage of not being completely myopic. You can actually learn the rules of winning tic-tac-toe. And the accuracy, of course, is perfect because it actually learned what constitutes winning here. So I'm going to take a little bit of a digression. Whoops. Yeah, a real digression. Wow. Sorry about that. So what happened was my computer was sliding gradually off the podium, and I kept kind of pushing it back on, but anyway. So I may have to do that again. All right. So I don't know why they slanted it. It's like your laptop just, anyway. Okay, so I'm going to take a little diversion and talk about the complexity of the set of rule lists from pre-mined rules. So A is the set of all possible left-hand sides of rules. So remember that. So the set is A. That's the set of rules that you essentially mine. So you got a pile of rules. Now think about a function g. It's a scoring function. It eats a rule, so a left-hand side and a right-hand side, and it produces a real valued score for each rule. Think of capital G as the set of all scoring functions. Fg of x is actually the evaluation of the decision list for the point x. Okay, so essentially, you score each rule by the function g. That produces a decision list. And then to get the label for point x, you send it through the list. You find the highest scoring rule that it applies to and get the label. So pick out the argument of the highest scoring rule that x applies to. Okay? So this is my decision list classifier. Fmax score is the set of all of these decision lists. So think of Fmax score as the set of decision lists. And what I want to do is bound the complexity of the set Fmax score. Why do I care about that? Because I want a generalization bound. A generalization bound is a bound on the true error, the true risk, which is the expected misclassification error on the distribution that the data are drawn from. However, I cannot calculate this because I don't know the distribution the data are drawn from. But what I can calculate is the empirical risk, which is the fraction of misclassified points. So the way these learning theory bounds work is that you get an upper bound on the true risk in terms of the empirical risk and some complexity measure of this set. So that's why I want that. Okay, so here's the result, which is that the VC dimension of the set Fmax score is exactly the size of the set of left-hand sides of rules. Okay? So to me, this is meaningful because the VC dimension of the set of linear models, like what we were seeing yesterday, is actually the set of the number of features plus 1. So I'm essentially saying that these decision lists, the class of decision lists, has essentially the same expressibility power as the set of linear models. So I don't have time to go through the whole proof of this, but I will do the first part. So the first part, first I want to define VC dimension for those of you who forgot what it was. So VC dimension of F is the cardinality of the largest set of points that can be shattered by functions in the class. F shatters a set of points if for all possible assignments of labels, there's a function in F that makes no errors. So in other words, the VC dimension is the size of the largest set of points that can be classified in all possible ways using functions from the class. So the first part of the theorem is that the VC dimension of Fmax score is less than or equal to the size of A. And the other half, part 2, is that it's greater than or equal to the size of A. So let me just show you the less than or equal to part. So what do I need to show here? I need to show that if you give me any n points, where n is bigger than the size of that set A, then there is a labeling that cannot be realized, cannot be shattered, for any function in this set. Okay? So I have to construct that labeling for you, for these points. So here's how I'm going to do it. I'm going to take each point, and I'm going to represent it in rule space. So I'm going to set xij bar to be 1 if rule j, or item set j, xi is captured by that rule. Okay? So if that item set is in that observation, then xij bar is 1. Okay? So now what I've done is I've taken each x, and I've taken it from its original space, and I've represented it as a point in the set R to the size of A. But there are n points, and n is bigger than A, the size of A. Okay, so that means that these points are linearly dependent. So that means there's coefficients that are positive and non-empty disjoint sets, M0 and M1, so that I can create a linear combination of M0, the points in M0, and set it equal to a linear combination of the points in M1. Okay, so from there, I'm going to set A0 equal to the left-hand sides that are obeyed by the points in M0. And A1 is going to be the left-hand sides for the points in M1. Now, it turns out, which is not very hard to show, that actually A0 equals A1. So in other words, the points in M0 and M1, they actually obey the same sets of rules. So that actually gives us a lot of leverage here. Now, what I'm going to do is have you pick a scoring function, any scoring function, so any decision list you like from this set, and take the highest scoring rule, take the top rule in the list. So that rule is called A star. Okay? So A star has the highest score. It's the left-hand side with the highest score of rules in A0 and rules in A1, because guess what? They're the same. Take the highest left-hand side. Its right-hand side is Y star. Take any points that fit into that rule, and it's either in M0 or M1. What that means is that, so there's some point that's in M0 and some point that's in M1 that both fit into that top rule. And because of that, they get the same label. So that's how that's the kind of key thing that we need to construct this set of labels. So all we have to do is set all of the labels in M0 to be one thing and set the labels in M1 to be the other thing. So when we do that, there's no way our rule list can distinguish between these two. Okay? It'll classify them both the same way every time. And it doesn't matter which G you pick, it'll happen for all G. So this set of labels simply cannot be realized. And the VC dimension then is less than the size of A. Okay. So part 2, I don't have time to do, but what it involves is just constructing a set of points of size exactly equal to the size of A that can be shattered with functions from the set. Okay. So now, go back to a real-world example, which is we've been trying to beat the CHADS 2 score, which is probably the most widely used predictive model in medicine. It measures stroke risk among patients that have atrial fibrillation. So if you have atrial fibrillation, the doctor will very often give you your CHADS 2 score, which is your risk of stroke. The CHADS 2 score was originally developed using data from less than 2,000 patients with 5 features. Here they are. Recent congestive heart failure, high blood pressure, age, diabetes, and mini strokes, prior strokes, mini strokes. We had a major advantage over the CHADS 2, two major advantages over the CHADS 2 score. We had a better data set. We had 11.1 million Medicaid patients, 12,500 of which had atrial fibrillation. And we considered all drugs and conditions. So we had over 4,000 drugs and conditions. So we had over 1,000 times the amount of data they had. But we also had a better algorithm. Their algorithm was to put a bunch of doctors in the room and tell them to come up with the CHADS 2 score. Our algorithm was Bayesian ruleless. So we mined over 2,000 rules. And this is our CHADS-2 score. So the CHADS-2 score, our version of the CHADS-2 score says, if the patient has had this condition, which is like a very serious stroke causing paralysis on one side of their body recently, then their stroke risk for the following year is 58.9%. Else, if they've had cerebrovascular disorder, which in our data set is like a prior stroke, then they also have a very high stroke risk for the following year. Else, if they've had mini strokes, and so on. And I like this because it's very similar to the CHADS-2 score. It just goes into more detail on the patient's recent medical history. Now, this is accuracy. This is out-of-sample accuracy on 5 test folds. These are ROC curves, so you want to be closer to the top left. Black is Bayesian rule lists, the point estimate, the single model from Bayesian rule lists. This is the CHADS-2 score in blue, and then the green one is the CHADS-2 VASC score, which was designed as an improvement to the CHADS-2 score. I don't know how many of you are awake, but clearly that's not an improvement over the CHADS-2 score. It's much worse than the CHADS-2 score. And it just goes to show you the danger of constructing predictive models by hand. So, what?
I was going to ask this question.
Oh, okay. Yeah, so this is area under the curve, area under those ROC curves for the different learning algorithms we tried. The bottom line here is that CARD and C5 were actually worse than the CHADS-2 score. That's bad. The Bayesian rule list point estimate was a bit better. Actually, yeah, quite a bit better. And if we actually averaged over the posterior, so we lose the interpretability, but we actually, we're looking at the whole posterior, then we're actually on par with random forests, which was the best of the learning algorithms we tried. The training time, so we're not at the level of CART in terms of training time here. So CART was at 12 minutes. We were at 21 minutes. We're working on ways to speed it up, but for this particular application, that extra 12 minutes just doesn't matter. What? Okay, that's fine. So in terms of our current work, what we're doing is trying to speed it up, and we've already been able to speed it up about an order of magnitude over what I just showed you by taking Bayesian rule lists and using tricks from the field of systems, from computer systems, to try to speed it up. So reuse of certain computations, we're going to parallelize it, and hopefully that'll be released in, I don't know, a few months from now, hopefully. And then if you only want the map solution, if you only want the maximum a posteriori solution, then we're developing some interesting branch and bound methods where you can sort of provably exclude large numbers of rule lists from consideration because you can prove that you never need those lists. We've also been designing a version of Bayesian rule lists it's called falling rule lists. It's actually not a version of Bayesian rule lists. It's a separate model. And for this model, the rules are ordered like Bayesian rule lists, but the probabilities always decrease on the right-hand side. And so it stratifies the patients by decreasing risk. So if you want to look at the highest risk patients, then all you need to do is look at the top rule. And that's kind of useful for doctors because they want to be able to determine immediately whether someone's high risk. So they don't want to cruise through the whole list to figure that out. Another thing that we're doing is extending it to causal modeling. So a lot of times people interpret machine learning methods as if they were causal anyway. So they say, all right, if I change this feature, will this change my prediction? And the answer, of course, is no, unless the model was designed for that. So we've been designing a version that's causal, where we model the effect of the drug on the patient, so that the list, you can actually say, okay, if I change this feature, the effect of the drug is different. And this allows the user to act on the model in some sense in a causal way. We're also designing a version of the rule list that's optimized, that uses mathematical programming, in particular mixed integer linear programming. And then Tong, who is here in the audience, actually, where are you, Tong? There she is. She had a poster yesterday on ors of n. So these are logical models that are disjunctions of conjunctions, so disjunctions of rules. And this is sort of a Bayesian disjunctive normal form. In terms of some other applications, you know the method's working well when you can hand it to a bunch of undergraduates and master's students and say, go, and they get nice models without having to complain. So that's what we've been doing. So Jiming is my undergraduate student, Burke is a graduate student, and they've been working with me on designing classification models for recidivism prediction. This is where you want to predict whether someone is going to be arrested within a few years after they're released from prison and for what kind of offense. And then Will is a master's student, and he's been working with me and Randy Davis and a bunch of doctors to try to do early tests for cognitive impairment. So what they have people do is they have people draw these clocks. This is a standard test that you would take to determine whether you have a cognitive disability. And a normal person would draw clocks like this, and maybe if you have a memory impairment disorder, it might look like that. That's a bit of an extreme case, but you can detect these sort of subtle things to determine whether someone has a cognitive impairment. And we've been using Bayesian rule lists and falling rule lists to do this, to produce scoring systems for this test. And then the falling rule list paper actually has an application in it to readmission prediction. All right, last slide. So far, so good. We seem to consistently outperform decision trees. We're working on speeding it up so that there's not really a good reason to use CART as opposed to our methods. We want to produce predictive models that can fit on an index card. The nice thing about these logical models is that they're completely robust to outliers, unlike linear models. For our methods, there's little to no parameter tuning, no annoying nested cross-validation, and the parameters are all meaningful because they're simply the size and shape of the rule list. And they provide reasons for each prediction. You say, I predicted this because the features obey these conditions. Okay, that's it.
Hello.
Okay.
Hi. Hey, so you had the error bars on your AUCs?
Had what?
You had error bars
Yeah.
on your AUC. How did you compute them?
Well, we do so fivefold cross-validation, so you can get,
So this is T test error bars, T statistics error bars?
Yeah, we had a big discussion over whether to do statistical significance.
Okay, but these are from 5. This is basically the standard deviation of 5.
Yeah, of these 5 folds,
5 folds.
that are.
Okay, thank you.
The 5 folds that are here. Yeah.
Could David just set up his computer while we're answering a few more questions?
So I have a question about so I think you mentioned that the distribution for the number of conditions per rules, maybe it was a Poisson or something like that. Mm-hmm. Can you comment on the sensitivity of the model prediction using different distributions for that? And in many examples that you showed, I think there were 1 or maybe at most 2 conditions per rule, and I was wondering if your model allows for more and how the prediction changes as a function of those distributions of the number of rules, conditions per rules.
So that's a really good question. So it depends on the size of the data set, because those are just priors. They can be overwhelmed with more data. So for instance, for the experiment that we did with the CHADS2 score, we actually produced the models for the 5 different folds, and you could see that the models were very similar to each other. So it's not very sensitive to anything for that data set, but that's a rather large data set because it has 12,500 patients and 4,500 conditions. If it was a smaller data set, it could be potentially very sensitive to the user-defined parameters for the size and the shape of the list. We like to have only 1 or 2 conditions. In fact, sometimes we only mine rules with 1 or 2 conditions. But if you wanted rules with longer conditions, you could do that. You would have to set eta to be a little bit larger to favor those rules. But the Bayesian model averaging will sort of undo some of it. So that could that also kind of helps regularize it sort of implicitly. Let's see, how else can I answer that question? Yeah, okay.
So you're doing Poisson sampling on the space of rules, and so there can be some conflicting rules, so you're using only the first rule that every observation applies. So what is the ordering of your rules in a set of rules that you sample? Is it uniform, I suppose?
Yeah, so the model is that the size of the rule list is Poisson centered at your user-defined size. The number of conditions per rule is Poisson, but then the rules are chosen uniformly from the set of rules with that size.
Right.
So it's not favoring certain rules.
So this would be very similar to random forest because you're just averaging over a class of rules that are have a particular shape, essentially a tree of a particular shape. So the performance will also be very similar to random forest.
So I don't see this model as being anything similar to random forest at all, because random forest uses this greedy strategy that I'm trying to completely avoid. But I do agree that the complexity of the set of these models seems to be very similar to the set of complexities the random forest models. Yeah.